Question 6, we're going to tackle the wild slungs known as trig functions. Okay, this doesn't look nice to me. Let's color code it quickly. Yes, that's much better. Okay, now we're going to have a look at, we want the values of a and b, which are nested in the sine graph. So we're going to grab this quickly, and I'm going to explain what a and b actually do to the functions in terms of transformations. So we're firstly going to have a look at a. Now a can do two things. It can reflect the graph over the x-axis, or it can vertically stretch or compress the graph. And to actually figure out which one it's doing, or if it's in fact doing both, we need to know what the original sine graph looks like. So you've got to know this off by heart because it's not on your formula sheet. So your sine x graph has a wavy shape, and it starts at 0 and 0, and then it goes to a focal point of 90 and 1. So we can see it sort of goes up and then down, up and then down, so it has not been reflected over the x-axis. So we're going to get rid of that. And now we're going to have a look at if it's been vertically stretched or compressed. Now if I look at this point, it's normally at 90 and 1, but now all of a sudden it's at 90 and 5. So you kind of look at the distance from the middle of the graph to this point. We can see in this normal sine x graph, there's a distance of 1 over here. But in our new graph, there's a distance of 5 over there. And a is a factor that we multiply by. So we got to ask, what did I multiply 1 by to get 5? And the answer is 5. So a is 5 in this case. And that sorts out the value of a. Now we're going to sort out the value of b. Now let's go through what b covers. So b focuses on the horizontal stretch or compression of the graph. So for that we need to look at the period of our original graph as well as our new graph to tell what the value of b is. There's also a formula that you can use to get b, which I will go through. So if we look at the period of this graph, what we need to do is just focus on one wave, and by one wave I mean this. So you look at like one down and up part of the graph, like it's basically one wave is how often does it start repeating itself. So it's going to start repeating itself again after that and again after that. So this is like one repetition of the graph, call it that. And we can see from minus 180 to 180, that's 360 degrees long. And if we look at this graph that we have over here, it's also 360 degrees long, because this is one wave over here, and it spans the distance of 180 plus another 180, also 360. Which means that there's been no horizontal stretch or compression, which means b has to be 1. No stretch or compression underwent or took place here. So this times 1 gives me that. And the formula I was referring to earlier goes like so. So the coefficient of x, or the coefficient of the angle, in this case it's b, equals 360 divided by my new period. It's 360 for sine and cos, and it'll be 180 for tan. So the new period of this graph is 360. So 360 divided by 360 will give me the 1 that I've been talking about for b. And then just one last thing, we do have to state the values of a and b separately because they asked us to do that. So we just say a equals 5 and b equals 1. This was a very sneaky way of just saying get the equation for the green graph. Alright, so now I'm going to fill the equations in on my graph and move on to the next question. But firstly, let's have a look where the 2 marks come from. Can you guess that you just get 1 mark a pop here? There are no marks for working out. So let's move on to the next vraagstyle, bro. Okay, in 6.2 it says the graph of g of x, the blue graph, is shifted 30 degrees to the right and 2 units vertically down from the graph h of x. Determine the equation of h of x. So for this question, we take more of an algebraic approach. So I'm just going to grab the equation of g of x, and we're not going to need the diagram for this question. Again, I'm going to give you a quick crash course of where you add or subtract these two variables to achieve this. Okay, so if you have a look over here, A doesn't get affected at all. So this variable over here moves the graph left and right. If I'm moving it left, I add. If I'm moving it right, I subtract. And then this variable that's outside the bracket moves the graph up and down, and this one's normal. If it's positive, you're moving it up, and if it's negative, you're moving it down. So we're going to apply this logic here. This 4 won't be affected at all. And now I'm creating a new graph when I'm moving it. The new graph is called h of x. So g of x will change to h of x. And like we discussed, the 4 is not affected. Now I'm going to open up some brackets so I can move it left and right. And I'm moving it 30 to the right. So if I'm moving it right, I'm minus. So this is going to be minus 30. And then I move it 2 units down, so then I'm minus at the end of the equation here, so I'm just going to put a minus 2 over here. And there you have it, the question's done. I've successfully given the equation of h of x. Now let's have a look where the 2 marks come from. And you simply get 1 mark for the minus 30 and 1 mark for the minus 2. In 6.3, they want the minimum value of 8 divided by g of x in the interval from negative 60 to 60. So I'm going to zoom in on this interval on the graph. I'm going to ignore everything else on the graph. Okay, so now you can see I've restricted my graph from negative 60 to positive 60 as they instructed with this. And now I want the minimum value of 8 over the blue graph essentially. And to make that happen, you need to find out where g of x is the biggest, because you want basically 8 divided by the biggest number possible to give you the minimum of this expression. So we just kind of scope that out, and remember g of x is another way of writing the y value. So I want the biggest y value possible, and if I follow this graph, I can see it's here, it's 4. So the minimum of 8 over g of x will be 8 over 4. And 8 divided by 4 is just 2. And you only get 1 mark for this 2 in this question. Question 6.4 says if A has this coordinate, which has been indicated on the graph, we need to determine the coordinates of B, and B is sitting over there. Now we're going to use symmetry to make this happen. Quite an easy question. So let's go ahead and look at the y values first. Okay, now to get down here, I need to go down 3,12 units. And due to the symmetry of these points, I need to go up 3,12 units to get to B. Which in turn gives me the y value of B, it's 3,12. And now we're going to focus on the horizontal shift to get to A. Basically, I'm going to look how much I went that way or that way. And it's going to be the same as how much I go that way to get to B. So what I'm going to do is find out how much I went from minus 180 to get here to A. And then it's going to be the same distance as how much I go from 0 to get here to B. So let's have a look how much we went that way. Alright, I do not have the brain power to do that mentally, so I'm going to lean on the calculator to help me out with that. Then just remember the length of a horizontal line is the one on the right minus the one on the left. So I'm just going to type that in on my calculator. And then just remember to use brackets when you do that, because you're going to have a minus minus. And if I press equals s to d, I get 38,66 degrees. And due to the symmetry of these points, it means I have to go 38,66 degrees that way to get to B. Which ultimately gives me the x value of B. If I go from the x value of 0, 38,66 degrees that way, it's just going to be 38,66 degrees. And for this question, you just get 1 mark a pop here, so you get 1 mark for the correct x value and 1 mark for the correct y value. Question 6.5 says, for what values of k will f of x equal k have no real solutions? F of x is the green graph, so I'm kind of going to ignore the blue graph. And then k can be various things, but in this instance, if f of x equals k, the best thing to do is picture k as a horizontal line. So it's best to visualize k like this, a horizontal line. And they want you to place this horizontal line somewhere so that you're going to have no real solutions when it equals the green graph. So currently where k is placed, it touches the green graph twice, so there is real solutions. You want to move it up or down enough so that it does not touch the green graph and therefore will have no real solutions. So I want to move k kind of up here, kind of up there, so it doesn't touch the green graph. So now you'll never have solutions. You'll never get this purple line touching the green graph. And the threshold for that is over here. If I move k above this y value of 5, it will never touch the green graph. And we're going to get another sort of contrast at the bottom of the graph. If I move it down past this value, it will never ever touch. So if I move k down here and past over there, it's never going to touch the green graph. So our focal points are here, 5 and minus 5. And we can formulate our answer in one of two ways. I'll show you both. So the first way I can say it is k is an element from minus infinity to minus 5. It's saying like k can be anywhere under minus 5. And a different way of saying that is k can be smaller than minus 5. It can go from minus 5 downwards essentially. And then the other part of this is when k can be greater than 5, so I can make k equal 5 or it can be bigger. Now I use round brackets because it can't equal 5, because if I put it on 5 I will get a solution of 90 over there. So I have to use circular brackets or the inequality symbol that does not have the equal sign, and this one just kind of states from 5 upwards, so anything bigger than 5. And let's have a look where our marks come from here. Okay, you just get 1 mark per little solution here. So this inequality gets a mark, this inequality gets a mark, or if you used the different notation, this will get a mark and this will get a mark. 6.6, we need to use the graphs to determine the values of x in the full interval from minus 180 to 180, for which f of x is smaller than g of x. Okay, let's break this down and translate it to English. Alright, so now you've got to remember the crocodile always eats the bigger graph. So they're basically asking you, where is the blue graph on top of the green graph? And you use the crocodile mouth to tell who's on top. So I see that happening from here to here. So it starts here and it ends over there. And bear in mind, when we give our answer, we only use the values of x. Now I believe we got the coordinate of b earlier. I'm going to grab it quickly for us because we are going to need it to answer this question. Okay, now that b is there, let's have a look at how we write that up. There is 2 possible methods of writing it up. I'm going to go through both of them. So the first possible way of stating it is x is an element that starts at minus 141,34 and ends at 38,66. I use round brackets because this crocodile mouth, aka an inequality symbol, does not have the equals to sign there. The second way of stating it is saying x is in between these two values and both the inequality symbols eat the oak on the right. So you can see this crocodile mouth eats the guy on the right, and this crocodile mouth eats the guy on the right. So you don't have to write both of these, just one of them will do. Use the one that makes more sense to you. And lastly, your 2 marks over here come from the correct endpoints, where you start and end, and the correct notation, actually formulating the answer correctly. And now we have officially reached our challenge round. 6.6.2 says, where is f dash of x times g of x greater than or equal to 0? So let's break this down and convert it into English. Okay, this one is a bit of a nasty little bogged down prawn. Right, so f dash x converted to English, it's the gradient of the green graph. F dash is representative of gradient. G of x is representative of the y value of the blue graph, and when they say greater than or equal to 0, That's another way of saying where is it going to give me a positive number or 0. Now we're going to start analyzing all the way on the left of the graph and make our way all the way across. So if we start analyzing over here, the green graph has a negative gradient. And if I look at the y value of the blue graph all the way on the left here, it's got a negative y value from there to there, because it's underneath the x-axis, which means the y value is negative, as you can see with these negative numbers here. So from negative 180 to 90, we're getting a negative gradient times a negative y value, and a negative times a negative will indeed give me a positive. So it's working from there to there. So let's formulate that quickly. And remember, there's two possible notations. I can say x is an element that starts at negative 180. I'm using square brackets because we do have an equals to sign over there. And that will entail using the same inequality symbol down here. Okay, now we're going to analyze after negative 90 what happens. So let's firstly have a look at what the gradient is doing for the green graph. So going from left to right, imagine you're driving a car on top of the graph. You can see I'll start to go uphill now. So this gradient is all of a sudden positive now. And then we need to analyze the y value of the blue graph. So after 90, it's got a y value that's positive for quite a while. So from negative 90 to 90, it has a positive y value, which means that I'm getting a positive times a positive, which will give me a positive. I've got a positive y value for g of x and a positive gradient for f of x. So from 90 to 90 it's working. So it carries on working all the way through. So I'm actually going to extend my endpoint here like this. It no longer ends at negative 90, it ends at 90 now. So it's working all the way through to there. Okay, lastly we're going to analyze this last little bit of the graph. Let's have a look at the gradient of the green graph. So we can see after I go over this turning point, the gradient becomes negative for the green graph. And if I analyze the y value of g of x, we can see it goes under the x-axis, so the y value is negative again. And a negative times a negative will also give me a positive. So it carries on working past 90 all the way to 180. So our ending point is not actually 90, it's 180. So we finally got the answer. X is an element that starts at minus 180, ends at 180, or I can write it like this, where both the crocodiles are eating the bloke on the right, just to help you remember that notation. And our 2 marks, let's see where those are coming from. Okay, much the same as the last question, the end points, so the correct starting point and the correct ending point, as well as the correct notation. Did you formulate these correctly? That question was hectic. If you're a strong student, then I would recommend you try to tackle these at the end of the question. But if you're like a weaker student, you're okay to like leave these out, and only if you have extra time, try them at the end. In question 7, we've been given a triangle TQR, which represents 3 points on a horizontal plane, which basically means it's on the floor. Triangle TQR is on the floor or on a flat plane. And we've got a flagpole PQ, and that will form a 90-degree angle with the floor, as they did illustrate for us. All the information they supplied over there is on the diagram, quite luckily. And now we need to express theta in terms of alpha and show that sine of theta is equal to sine of 2 alpha. Now to do that, we need to work in the triangle that has theta as well as alpha, and that's the bottom triangle TQR. We can see a theta there and an alpha there. So we're going to ignore the other triangle for a second. And if we're in triangle TQR, you might notice that this length TR is the same as this length TQ, because they both denoted with a variable y, so they must have like the same value. If y was 10, both of these sides would be 10. So we actually work in an isosceles triangle, and I like to mark it off on my sketch like this. And after I marked it off, a little bit of Euclidean has entered into the picture. Okay, now what do we know about isosceles triangles? The opposite angles are equal. So this over here will be the same as this angle here, alpha. And this is the Euclidean theorem that dictates that angles opposite equal sides. You're not expected to give reasons within trigonometry, so we're safe not to give a reason over here. So now we know that all the angles inside of a triangle add up to 180. So let's formulate an equation that says that. And how we formulate that is this angle plus this angle plus this angle all equals 180. Right, now I need to express theta in terms of alpha. What that means is get theta on its own. So let's go ahead and start doing that. Alpha plus alpha is just 2 alpha. 1 apple plus 1 apple is 2 apples, my bro. And then to get theta on its own, I'm just going to move that 2 alpha to the other side and it becomes minus 2 alpha. And now the first bit of the question is done. Express theta in terms of alpha. Done. Theta equals 180 minus 2 alpha. And now we need to show that sine theta is equal to sine of 2 alpha. So it almost looks like this, but I'm missing sines. So what I do is introduce sine on both sides of the equation like this. So in front of this theta, I just put a sine, and in front of this, I put a sine, but just make sure to wrap it in brackets. Now over here, I see a 180 minus. The alarm bells are ringing for reduction. So let's grab a cost diagram and do that quickly. And we are in the 180 minus quadrant. In the 180 minus quadrant, sine is positive. So this is just going to change into sine of 2 alpha. And we've arrived at the finish line. Sine theta equals sine of 2 alpha is exactly what they asked us to prove. Yes, you had to fight hard for these 2 marks. Alright, so this line over here, sum of the angles inside of a triangle gets you your first mark. And your second mark will come from sining both sides, if that makes sense, introducing sine on both sides. You don't get a mark for this because they gave that to you. And 7.2 says hence. When I see this word hence, hey baba, you gotta look at your last answer. They're telling you, use this to help you, Chana Bean. Prove that in triangle PQR. Alright, let's get rid of the other triangle. We're only working in PQR now. We need to prove that PR is equal to this trig expression. So PR forms the hypotenuse of our triangle, and we are working in a 90-degree triangle. We're on the nice side of town, bro. In a 90-degree triangle, we've got 2 tools at our disposal. We have the very infamous Pythagoras, as well as the classic Sokotoa. Right, we only use Pythag when we've got 2 sides and we're missing a third, so we're not going to be using Pythag. So we are using the infamous Sokotoa. Alright, so I want the hypotenuse. I want to get PR, so we've got to do something with hypotenuse. So it's either going to be sine or cos. And we also want to tie in the information we have. So we've got to use this x somehow. And x is the adjacent to my angle. It's adjacent or next to this theta. So we will be using cos because we have the adjacent and we want the hypotenuse. Okay, so this is already our angle theta. The adjacent side is just x, so we fill in x there. And the hypotenuse of our triangle is PR, so we just fill in PR there. Now I want to get PR on its own, so I can literally just swap it with cos theta. It's a shortcut of cross multiplying. I'll show you the long way quickly in case you are interested. So you put cos theta over 1 like this, and then you multiply going up. So I bring this 1 up. 1 times x is just x. And I bring this PR up. PR times cos theta is just PR cos theta. And then from here you divide both sides by cos theta to get PR by itself. And then these causes cancel as we planned for, and x over cos theta cannot be simplified, so there you have it. And a shortcut of doing all of that is this. You literally just swap the positions of cos theta and PR to get there. So you do want to get comfortably enough to make that adjustment. Okay, now this is, it's not quite looking like that, but it's got some aspects we want. It's got a cos theta at the bottom. This one has a cos theta at the bottom. So we need to transform this x into this trig expression using the other triangle. So now we divert our attention to triangle TQR, and we want to get an expression for x that mimics this format. So we're going to ignore triangle PQR and work with triangle TQR. Okay, now that we're in triangle TQR, we are in the cuck side of town. There's no 90-degree angle, which makes our job significantly harder. If there's no 90-degree triangle, there's 3 rules or formulas that you can apply. I'm going to show them on the screen now. They are called the sine rule, the cosine rule, as well as the area rule. Okay, and we need to get an expression for x. My first instinct is to always use the sine rule. I don't like using the cos rule and the area rule. I only use them under these circumstances or if they ask me for the area. So we are going to be using the sine rule because we've got enough information. We know all the angles here and we know all the sides of this triangle, so we've got enough information to actually choose which rule we want to use, and the sine rule is the simplest. So I'm going to get rid of the other 2 rules, and I'm going to walk you through how to use this thing. Now on the formula sheet you get given all 3 of these. We only use 2 at a time, so I'm going to get rid of this. And on the top here we need to put in the sides of the triangle. So we need x, we need to change this x to 2y cos of a. So I'm going to change this to x, and then at the bottom must be the angle opposite it. So at the bottom will be sine theta. And inside of this side an angle, I'll just choose another one. I can choose this one or this one. It'll lead to the exact same outcome. So I'm going to change this side to a y, and then opposite that y is alpha. So it's going to be y over sine of alpha. And now I've successfully implemented the sine rule. Alright, so the mission is to get x on its own here so that I can put it in there and hopefully get this. So I'm going to move the sine a to the top on this side. I'm going to basically cross multiply, but only with one of them. And I did make a small mistake there. This should be theta because x is across from theta. Sorry about that. Takes that sine theta up, and then we've got y sine theta over sine alpha. Now this word becomes important, hence. So this sine of theta here, I'm going to change it to sine of 2 alpha. And I knew to do that because of the word hence. Hence means use your previous answer to help you. I was getting quite stuck here. I didn't know what to do. So if I look at hence, I can change sine theta to sine 2 alpha. And now there's a double angle, my bro. 2 times alpha, you're doubling the angle. So let's grab the double angles quickly. And quite thankfully for sine of 2 theta or 2 alpha, there's only one double angle that's applicable. It's the last one. Alrighty, we are making some progress. We changed that sine of 2 alpha into 2 sine alpha cos alpha using this double angle formula that is on your formula sheet. And now we have a 1 term over 1 term, so we can cancel the sine of alpha and this sine of alpha. The sine of alpha, they get out of here, bro. After we cancel these sines, then 2 times y is just 2y, and we glue that cos alpha on there. And now finally we can change this x to 2y cos of alpha. And we have finally proved what they asked us to prove. PR is equal to 2y cos alpha over cos theta. PR equals 2y cos alpha over cos theta. Sure, quite a nasty little one. So this was the nice side of town, the 90-degree triangle. This was the ugly side of town where we had to use the sine rule. You get 1 mark a pop for using cos as well as the sine rule. Expanding the double angle as well as the cancellations of sine alpha to simplify. Then your final answer does not get a mark because it is given to you. In question 7.3, they've asked us to calculate the area of triangle TQR, and they've given us the following information. So I'm going to get rid of the other triangle. Let's just focus on triangle TQR. And additionally, I'm going to get rid of alpha, x, and y and replace them with the actual numbers that they supply to us. And I'm tempted to use area equals half base times perpendicular height, but I don't see a perpendicular height. So it's going to force us to use the area rule. So let's grab the area rule quickly. Okay, so with the area rule, there's a small term and condition that you've got to adhere to. If you're going to use the area rule, you've got to use 2 sides and the included angle. So I'm going to go to the angle I know, and then I have to use the 2 sides that are next to the angle. So I'm going to have to use the 15 and 20, and I'm literally just going to sub it in here. Okay, so when I sub in the sides A and B, it can be in any order, because you're multiplying everything in this formula, and the order of multiplication doesn't matter. So I'll just put the 15 first and the 20 second. And then inside of the sine, I've got to put the angle in between those 2 sides, which is 49 degrees. And once you've subbed that in, you pop that straight in your calculator. And if we press equals, we get 113,21. And bear in mind, we are working in meters here, and area will be meters squared because it's 2 dimensions. And having a look at your 3 marks, 2 marks purely come from substituting into the correct formula, and the last mark comes from the correct area with the correct unit. In question 8, we start off with the Euclidean geometry. All the info that's been listed is given on the diagram, with the exception that BC is a tangent to the circle. I like to mark that off. It just helps you apply theorems a little bit better if you mark that off. Your brain can see it a lot faster. So to get A1, we're going to apply the tan chord theorem. Let me show you what that's all about. So the tan chord theorem states you have equal angles that exist between the tangent and the chord, as well as the angle that is subtended by the chord. So you follow that chord down to the circumference, and then you get the angle that will be equal to this one. So if we apply that here, our chord is dB. And after recognizing our chord, we follow that down to the circumference. And when we follow that chord down to the circumference, it takes us to A1. So A1 will be the same size as this angle between the tangent and chord, which is 22.5. And now we've successfully applied the tan chord theorem. Okay, so how we write that is quite easy. We simply just state the size of A1 to be 22.5, and then we list the reason to the right of it, the tan chord theorem. And then this question is worth 2 marks. You get 1 mark for your statement and 1 mark for your reason of the tan chord theorem. In the next question, we need to find the size of D1. And D1 is located over here. So I'm seeing something happening quite close by. I see an isosceles triangle. So let's use that to our advantage. So the theorem we apply here, if we have equal sides in a triangle, then we have equal angles located at the base of the triangle. So I know that this angle C is the same size as this, 22.5. And when we state that C equals 22.5, we're going to use this as our reason. Angles up equals sides. And now to get D1, we're going to use exterior angles of a triangle, because D1 is the exterior angle of triangle CDB. And just to walk you through that theorem, to get the exterior angle, you go to the opposite interior angles add them together, and then they give you this outside one. So you can see in this example, 40 plus 70 gives me this 110 degrees over here. So to get D1, we go to the opposite two interior angles, add these guys up, and we get D1. So 22.5 plus 22.5 will give me an elegant 45 degrees over there. And this is the best way to write it up. You just say D1 equals the opposite two angles added together for the reason of exterior angle of triangle, and then you just simplify that. You can also pop it into your calculator to triple check, and we get D1 to be 45, which I have indicated on the sketch. And your 2 marks in this question are awarded from the statement and reason in this first line with the angles opposite equal sides. It's a fancy way of saying isosceles triangle. And D1 equals 45, 1 mark gets awarded for that statement, actually answering what they asked you to. 8.1.3, we need to get the size of B2, which is sitting over here. Okay, and now I recognize B2 is touching this line. This is quite a special line. It's a radius. And there's a very commonly used theorem with a tangent and a radius. And that theorem is called tan perpendicular to rad. It's not the first time we've seen it in this paper. So, if I have a radius and a tangent that are touching each other, there's a 90-degree angle that exists in between them. So I know that there's a 90-degree angle over here. And then, if I want to state that in my work, I've got to say the angle OBC is equal to 90 degrees. There's a lot of angles at B, so you've got to be very specific as to which one is 90 degrees. And when you list OBC, just make sure to put a copy over the B. It's kind of telling the person marking your work that the angle resides on the letter B. So the angle is by B over here. And then to get B2, we know that both of these, this 22.5 as well as B2, added together, they give us 90. So it stands to reason to get B2, I can just say 90 minus 22.5. And don't take chances with that, just pop it straight in your calculator and it will give us 67.5 degrees. And the 2 marks in this question come from the correct reason of saying tan perpendicular to rad, as well as your final answer of 67.5. This line does not need a reason, just by the way. In 8.1.4, we need to get the size of O1. O1 is sitting over there, and it's at the center of the circle, which is quite a big clue as to which theorem we're going to use. Now, if we have an angle at the center and an angle at the circumference, we can apply the following theorem. The angle at the center is 2 times the size of the angle at the circumference. It's a little bit difficult to see with this one, but it kind of looks like a bow tie. And with this bow tie, you've got 3 points on the circumference and 1 point is at the middle of the circumference. So this one at the center is 2 times the size of the one at the circumference. If you kind of follow this 45 back down to its chord, you get to BA, and then you can follow BA back up to get to O1. So this 45 and the O1 are subtended by the same chord. So we can just jump ahead and say O1 equals 2 times 45 for this reason over here. Angle at center equals 2 times the angle at circumference. Just like this, and 2 times 45 will give me a classy little 90 degrees over there, boss. Alright, let's fill that in and move on. And just before we move on, one thing teachers do appreciate is just stating the relationship with the letters first. So saying that O1 is 2 times the size of D1 and then actually filling D1 in as 45 degrees. Yeah, the teachers do appreciate that. It is good to put in your work. Okay, the 2 marks. One mark comes from the reason, and the second mark comes from the answer of 90 degrees for O1. In 8.2, we've been asked to prove that line OA is parallel to CB, and you've got about 4 ways of doing that. The best place to start looking is to prove one of these 3 things. So if I prove the corresponding angles are equal, so like if I make an F and I prove that these angles are equal, that adequately proves that the lines are parallel. Conversely, so if I prove that the co-interior angles add up to 180, that will also prove that the lines are parallel. And lastly, if I prove the alternating angles are equal, that will also adequately prove that the lines are parallel. So what I normally do is I highlight these two lines and see which one of those I can create. So if I highlight those two lines, I can't really make an F anywhere. If this line was extended, I could make like a sideways F, but that's not happening. I can make a U, but the problem with that is I don't know A2 and B1, so that's going to create a lot more work for me. But I can just join up these two lines to create a Z. And if I do that, would you look at that? The alternating angles are already equal. B2 is 90 degrees and O1 is 90 degrees. So we're definitely going to be heading down this route. The alternating angles are equal. And we just start off by showing that we recognize that those two angles are equal. So we're going to say angle O1 is equal to angle OBC. And we did prove that they were both 90 in previous questions. So you can see we proved O1 was 90 in this question. And for 8.1.1, or one of these questions, sorry, it was in this one, 8.1.3, we proved that OBC was 90 because of tan perpendicular to rad. So we've proved this above. So what we put down as our reason for this statement is proven above. And now we can jump to our conclusion that OA is parallel to CB. And our reason for knowing they are parallel is the alternate angles are equal. So we put this as our reason over there. And having a look where the 2 marks come from, this statement showing the link between the alternate angles gets you your first mark. And the reason of the alternating angles are equal gets you your second mark. And 8.3 gives us the length of the radius to be 12 units, and with that we've somehow got to calculate the length of BC, the tangent. So we did recognize earlier that this is a radius, so that will have a length of 12 units. And then I see another sneaky little radius over here, OA. Okay, and let's go through how we express that to our teacher. We just say OB equals OA equals 12 units radii. And I'm also noticing both of those are in a 90-degree triangle. And a 90-degree triangle is the nice side of town. I've got 2 tools at my disposal. I can either use Pythagoras or I can use SOHCAHTOA. Since I don't have any angles inside of this triangle, OBA, I'm not going to use SOHCAHTOA. I'd rather use Pythagoras because I've got 2 sides and I'm missing the third. So I'm going to calculate BA with the use of Pythagoras. Now my hypotenuse is the side AB, so I'm going to fill in AB in the hypotenuse's place. And just how to structure your work, you want to put Pythagoras as your reason. So I've just put Pythagoras over here. And then the other 2 sides just get filled in over here, so that's the 12 and the 12. So I'll put 12 in over there and 12 in over there. Okay, and then 12 squared plus 12 squared, I believe it's 288, but let's double check it with our calculator. So you just pop that in, press equals, some crispy mental maths there. Okay, so AB squared is 288, and then I'm just going to square root both sides to get AB on its own. So if I just square root 288, it's going to give me the length of AB to be 12 root 2, and I'm going to leave it in that format. Okay, we are getting somewhere. Now I somehow need to link this side to this side, and we're going to do that using the triangle ABC. It's quite a special triangle if you haven't noticed already. The base angles are the same, which means that these 2 sides must be the same length. And the Euclidean geometry rule that dictates that if I have equal angles down here, then those 2 sides must be equal. So I have equal angles over there, which means that BA must be the same length as BC. And we do have to kind of state a few things to convey that message to the person marking our work. So firstly, we need to show that we recognize the angles are equal. So I'm going to say A1 equals C, and that was proven in previous questions. We got this 22.5 and this 22.5 from previous questions. So we're going to use the reason proven above. And we state it just like that. A1 is the same size as C, which is 22.5, and we did prove that above. And now we jump into our conclusory statement that AB has the same length as CB, and we just simply say AB equals BC. And our reason for concluding that is what we spoke about earlier, sides opposite the equal angles. So this side is opposite that equal angle, and this side is opposite that equal angle. And now we have the length of BC, and we've successfully answered what they asked for. And I also like to be a bit overly cautious with these questions. I like to give the decimal value as well. So if I just press S to D, I'm also going to say 16,97 units underneath the root or the third form. And lastly, we're going to have a look where our 4 marks come from. The statement and reason for Pythagoras gets you your first mark. The answer for AB gets you your second mark. The statement and reason for the isosceles triangles, saying that this side equals that side, gets us our third mark. And the answer of, you can either do the third form or the decimal form, will get you your fourth mark. Jumping into question 9, we've been given a circle. We've been told that we've got a diameter BE, and we've got a tangent DA over there. And we've been told that these two lines are perpendicular, which has been indicated on the sketch. And first up, we need to prove with reasons that ABCD is a cyclic quad. Okay, I'm going to highlight that cyclic quad quickly. And now I quickly want to run through the 3 different ways we could possibly prove a cyclic quad. So the first method of proving a cyclic quad is if you prove this interior angle equals the opposite exterior angle, then you've got a cyclic quad on your hands. So over here, that would entail that proving the whole of C is equal to A1. Now I can't really get C because it's outside of the circle, so that's going to entail a lot of hard work to pull that off, and it might even be impossible. So I would prefer to run through the other methods of proving a cyclic quad because it might be easier. In the second method of proving a cyclic quad, if you prove that the opposite angles add up to 180 degrees, that adequately proves you have a cyclic quad. So that would mean proving the whole of B plus the whole of D equals 180, or I could do the whole of A here, or A2 and 3, plus the whole of C equals 180. But I don't know a lot of information about those angles, so I'm going to opt to go for the last method of proving a cyclic quad, which is converse angles in the same segments. If I prove that these angles are equal, then it adequately proves I have a cyclic quad on my hands. And I'm going to do that. You can kind of see this is the bow tie. Angles in the same seg, the nickname for it is the bow tie. So if I prove a bow tie over here in this blue cyclic quad or quadrilateral, then it adequately proves it's a cyclic quad. So I'm going to show you the bow tie that I'm seeing. So I've highlighted the bow tie in red. And they told us that this angle is 90. So I've already got one angle from the bow tie. So if I prove this angle here, A2 is 90, then it's a cyclic quad. And it has to do with this little bit of information, diameter BE. So one of my Euclidean theorems states, if I follow a diameter down to the circumference, I get a 90-degree angle. So we're going to do that with diameter BE. If I follow diameter BE down to the circumference, it takes me to A2. So I know that A2 is a 90-degree angle, and this is my reason, angles in a semicircle. And now we can see the angles in the bow tie A2 and D2 are matching up. And we just need to show that link to our teachers. So we just say A2 equals D2 equals 90. No reason is required for that line. After we've made that link, we're going to jump to our conclusion that the blue figure ABCD is a cyclic quad. And my reason for that will be the one we discussed earlier, converse angles in the same seg. And lastly, let's just have a look where the marks come from. Stating that A2 is 90 due to angles in a semicircle gets you your first mark. The link between the two angles that are 90 gets you your second mark. And the third mark comes from the correct reason associated with why ABCD is a cyclic quad. In 9.2, we've been asked to prove that BD bisects angle ABC. So they're asking us to prove that BD cuts this angle ABC, so this angle, in half. So in essence, what they're asking you to do is prove that B1 is the same size as B2. So firstly, we're going to have to do the tan chord theorem to pull this off. And earlier on, the question told us that this line DA is a tangent, and I somehow want to tie in angle B1 to that. So if I follow the angle B1 down to its chord, it takes me to chord AE. So the angle between the tangent and the chord, so A3, will be equal to B1. And now I somehow need to prove that B2 is also a green angle. And remember, this blue figure is a cyclic quad. We proved that in the question previously. So if we just apply angles in the same segments, we follow A3 down and we take it up to B2. Just to exaggerate a little bit further on that, if I follow A3 down to the end of the cyclic quad, and then I follow it back up to B2, we can see that A3 and B2 are equal because of angles in the same segment. That's one of the visual clues you can use. You can also use the visual clue of a bow tie. You can kind of like draw a bow tie and see it as a bow tie. And our bow tie would have looked like this. So we can see that A3 is equal to B2 because of the bow tie. Okay, let's have a look how we write that down. So firstly, we're going to say A3 is equal to B2 because of angles in the same seg, aka the bow tie. And then we need to show how we knew that A3 was the same size as B1. That was through the use of the tan chord theorem. And we write that up just like this, A3 equals B1, tan chord theorem. And now we need to make the link between these two. So I literally just say, therefore B1 equals B2. They're both green angles. And then I just do a conclusory statement and say, therefore BD bisects angle ABC. And lastly, having a look at the marks, we have 1 mark for this statement, 1 mark for this statement, and 1 mark for this reason. Lastly, in question 9, we need to prove that EC is a tangent to the circle OEF. So EC is over here, and they want us to prove it's a tangent to the circle OEF. Now there's no circle around OEF, so if it helps you, you must draw it. So if we had to draw the circle OEF, it would kind of look something like this. And to prove that this is a tangent, we need to prove the converse tan chord theorem. And what I actually need to do is prove that these angles are equal, and that will make this line a tangent to that circle. So in the context of our question, I would need to prove that angle E3 is equal to O1. And that will adequately prove what they are asking us to do if we just prove that E3 is equal to O1. So I'm going to get rid of the circle and I'm going to start working on that. I'm going to start off with O1. Now I can see O1 is at the center of the circle, and I know there's an angle here that I've already dealt with at the circumference of the circle. So O1 will be 2 times the size of B2. And for that we used angle at center is 2 times the angle at the circumference. So the one in the middle is 2 times the one at the circumference. So we're going to put this as our reason next to this line. And now I'm going to focus on E3. If I can prove that E3 is 2 times the size of a green angle, then we've got a winner-winner chicken dinner on our hands here. What I'm noticing is that E3 is the exterior angle of this cyclic quad, EFBA. And I know a theorem that ties in the exterior angle of a cyclic quad to the opposite interior angle. And that theorem states that this exterior angle is equal to the opposite interior angle. So if we apply that here, this exterior angle of the blue cyclic quad will be equal to the opposite interior angle. So it's equal to this green angle plus this green angle. So it's 2 times the size of a green angle, my bro. And now in essence our job is almost finished. We've proved that E3 is the same size as O1. They both double the size of a green angle. And let's see how we're going to write that up. Firstly, I need to show how I got E3 to be double the size of that green angle. So I'll firstly just say E3 is equal to B1 plus B2 because of the exterior angle of a cyclic quad, as we discussed. But from the previous question, we know that B1 and B2 are the same size. So I kind of want to get E3 to look the same as this. So I want to change B1 to B2. But before I do that, I have to include a statement that says, but B1 equals B2. And our reason for that, it was literally proven in the previous question. So we just say proven above. Now I'm going to change this B1 to a B2. And after I do that, B2 plus B2 is 2B2. It's like x plus x is 2x. And after I've done that, you can see that O1 and E3 equal the same thing. E3 is 2B2, O1 is 2B2. Graphically, we've been saying O1 is 2 times the green angle and E3 is 2 times the green angle. So from that, we're just going to conclude, therefore, O1 is the same size as E3 like this. And last but not least, I now need to conclude that EC is a tangent to the circle OEF for the reason we discussed earlier, converse tan chord theorem. And we write it just like this. EC is a tangent to the circle OEF for the converse tan chord theorem as your reason. Right, let's have a look where the 4 marks are coming from. So your first mark will come from the statement and reason that's associated with angle at the center is 2 times the angle at the circumference. The exterior angle of cyclic quad statement gets you a reason. Making the link between O1 and E3 gets you your 3rd mark, and the converse tan chord theorem gets you your 4th mark. And just in case you wanted to see it visually again, I've drawn the circles, so now we can actually see the tan chord theorem in action over there. And that wraps up Frastal 9, my bro. In question 10, we've been given this diagram and we've got to prove the theorem which states that AD over DB is equal to AE over EC. So this is a proof that you've just got to know off by heart. So let's walk through it quickly. So normally you get given the diagram and then you just start with your constructions. So you have to start off with 4 constructions. You draw a perpendicular height that sits on AD and we name it perpendicular height 1. And we do a perpendicular height that sits on AE and we name it perpendicular height 2. Additionally, we join the lines or the points DC and BE. So we join up DC and we join up BE. The next step of the proof is we need to get the ratio of triangle ADE over the area of triangle DBE. So we are focusing on this triangle over here as well as this triangle over here. And now we're just using our standard half base times perpendicular height. So for triangle ADE, AD forms our base and our perpendicular height is perpendicular height 1. And then for triangle DBE, DB is our base and the height of the triangle sits outside of it. This is the perpendicular height for triangle DBE. Then from there, we can see that they have the same height, so they cancel. Additionally, the halves also cancel. And we are just left with AD over DB. Now we're going to do a very similar thing with another 2 triangles. Before we move on to the next set of triangles, we've just got to say same height as our reason for that, because we recognize they have the same perpendicular height. Now we're going to direct our attention towards triangle ADE, so the same one ADE, as well as triangle EDC. So we've got EDC, so we're using that triangle now. And in a similar fashion, we're going to use half base times perpendicular height, but we're going to use perpendicular height too. So to run through that quickly, for triangle ADE, this will be your base, which is AE, and then this is your perpendicular height, so it's perpendicular height 2 over there. Then for triangle EDC, this will constitute as your base, EC, and the perpendicular height will lie outside of it there, so it's perpendicular height 2. Once again, the halves cancel, the perpendicular heights cancel, and we're left with AE over EC. And our reason there, we have to put that they have the same height for these to cancel adequately. Next up, we're going to write a statement saying that the area of triangle ADE is the same as the area of triangle ADE. I know it may seem a bit silly, but it is important to prove this. And then we're also going to state that this triangle, DBE, has the same area as this triangle, ACD. And our reason for knowing that is because these triangles have the same base as well as the same perpendicular height. So the base of these triangles is DE. You can see they share that side of the triangle. And then if I had to draw a perpendicular height that goes down here, it would be the same. Alright, once we've stated that, we're going to jump to this statement. We're going to say this ratio of areas is equal to this ratio of areas, just like this, because we proved that this is the same as that, as well as this is the same as that. And then we kind of replace this with AE over EC, and we replace this with AD over DB. So this gets replaced with this, and this gets replaced with this. And we just say therefore AD over DB equals AE over EC, and now we've adequately proved what they asked us to prove. AD over DB equals AE over EC. This proof is a bit of a bogged down prawn, I won't lie. It's a bit of a rough one to learn. And just to quickly run through where the marks come from here, you get 1 mark for your constructions. You get 1 mark for this statement over here. You get 1 mark for the correct statement and reason over there. Then you get 1 mark for these 2 statements and 1 mark for the correct reason over there. And then that forms your 5 marks. Jumping into question 10.2.1, we need to find with reasons the ratio of AC over FC. And we've been given a whole bunch of information here that has been adequately marked on the diagram. So these 2 lines are parallel, which have been marked by these arrows. These 2 lines are equal, which has been marked by these 2 little strokes. And we've also got a diameter, BG. That's quite a big clue. And first up, we need to find with reasons the ratio of AC over FC. So with these ones, you kind of want to work backwards. So I'm going to draw scallops over AC and FC. And we've got to use a grade 12 Euclidean Geometry theorem where we take ratios across parallel lines. We actually just did the proof for it. It's this nightmare of a proof. But when we take them across, we use the following theorem. And this theorem is more formally known as the proportional intercept theorem. And the reason we can say line parallel to one side of triangle, or we can say proportional intercept theorem and state the parallel lines. So with these ratios I've indicated with the curved lines, we follow them across the parallel lines, like this. So FC, the corresponding scallop, if I follow it down, will be over DC. And if I follow this parallel line down, I get the corresponding scallop over BC. And how we're going to state that is we firstly start by writing this. AC over FC equals. Okay, and then AC is the big scallop on this side. So I put the big scallop on this side, which is BC on top here. When I say scallop, I just mean curved line. So this curved line here, I'm referring to as a scallop. And then FC is the small scallop. So we do the small scallop here, which is DC. And now I somehow want to try find the value of this. So BC over DC. Now remember they told us earlier that BG is a diameter. So I know that BD is a radius and DG is a radius. So they have the same length. So I'm going to put a double stroke here by BD to indicate that. And how I communicate that in my work is I say BD equals DG, which is, for the reason of radii. And with that, I can conclude I've got a 1:1:1 ratio over there. And we can see that DC forms 2 parts of those 3 parts. So I can put a 2 here. And BC forms 3 of those parts. So I can put a 3 over the scallop. So if I have the ratio of 2:3 now, I can transfer that back across. So this one's also got a 2:3 ratio. And then when I take ratios across the parallel lines, it is quite important to state the parallel lines. So I'm just going to say AB is parallel to FD for me to actually apply that theorem I've been using, line parallel to one side of triangle. So the best order to kind of do it in is you state the radii first, then you state the parallel lines, and then you jump into your ratios. You should state your ratios after you show the parallel lines. But you kind of need to work backwards in these questions to actually know what to do. And then next to this, we can just hit a equals 3/2. And your 3 marks will come from stating the correct equal radii, this statement of making the ratios equal, and your reason for making the ratios equal, line parallel to one side of triangle. Next up, we've got to prove given reasons that triangle ABC is similar to triangle DEC. Let's get those triangles highlighted so we can see what we're doing better. Alright, that's a lot better. Okay, so to prove that 2 triangles are similar, we need to prove that all the angles are the same. And luckily with triangles, we can prove that 2 angles are the same, and then the third one is equal by default because of interior angles of a triangle. So in short, let's prove that 2 of the angles are the same inside of those triangles, and then the third one will be equal by default. Okay, now earlier on in this question, they told us we have a couple of tangents here. So they said AB and AE are tangents. So that's going to be very important to cracking this question, so I'm going to mark it off. Okay, now firstly, with these 2 triangles, I'm noticing they share a common angle. So how we say that is C equals C, common. And then that's one angle sorted out in both triangles. Now I just need one more angle in both triangles to be the same, and my job is essentially done. Okay, so firstly, in this orange triangle, I see a radius and I see a tangent. So tan perpendicular to rad, my chum. And just to give you a quick reminder of that, if I have a radius and a tangent, I know that the angle between them is 90 degrees. So here's a radius, here's a tangent, so I know this angle is 90 degrees. I can conclude it's 90 degrees. And we express that in our work like this. The angle ABD is 90 degrees because of tan perpendicular to rad. And now I see that happening again over here. Here's a radius and here's a tangent. So I know that E1 is 90 degrees for the exact same reason, tan perpendicular to rad. And just to show you that a bit visually, here's your radius DE and here's your tangent. So the angle between them is 90 degrees. And now I just want to make the link between these two. I want to show that these 2 angles are equal. So I just say therefore ABD equals angle E1. And after we've proved 2 angles inside of the triangles are the same, the third one will be equal by default. So the third one in the blue triangle will be D3, and the third one in the orange triangle will be angle A. So I need to show that they are equal. So I'm going to say angle A equals D3, and then I say int angles of triangle. It's a really good habit to get into to prove that two angles are the same, and then the third one will be equal by default always for this reason, int angles of triangle. Okay, now I'm going to jump to my conclusory statement. I'm just going to copy paste this over here. Triangle ABC is similar to triangle DEC, and my reason for knowing that is angle, 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 which you can write in one of two ways. So I can use three capital A's like this and just say A, or I can use the angle symbol, which is my personal preference, and I can state it like this, angle, angle, angle. So this symbol over here is short for angle, interior angles of triangle. So this will say angle, angle, angle. And lastly, let's have a look where the 3 marks come from. So your first mark comes from showing that C is a common angle between the blue triangle and the orange triangle. The second mark comes from showing how these two angles are equal. Your reasons do get marks over there. And the last mark comes from showing the link between the last two angles, the purple angles. And you don't get marks for this because it is given to you over there. Alrighty, welcome to your challenge round. Okay, now we need to prove this weird equation over here. DE squared equals AE times EC. Now the best place to start is you look upwards. Remember from the previous question we proved that these two triangles are similar. So with that we can extract ratios from them. When I extract ratios, I just kind of copy paste the statement. And then I do what I call the smiley face method. So I draw a smiley face over both of these things like so. And now I can extract my ratios quite a lot more easily. Now I can extract 3 ratios from these triangles, but I want to get the 2 correct ratios that entail sides that I have here. So I want the side DE. So I want DE in the picture here. So I'm going to use the left eyebrows. And I'll just write it like this, AB over DE, like so. And I also want EC in the picture here, so I'm going to have to use this EC, so I want the right eyebrow as well. So that's going to be BC over EC. I do the right eyebrow over the right eyebrow. And to correctly state that, I just write the ratios like this. With this as my reason. You must always use this to help you with these questions. Like 90% of the time, that's going to be the case. Okay, now we are getting somewhere. Now I'm going to kind of assess this compared to this, and I'm going to see what I want and what I want to get rid of. So I want these two guys to stay. I want DE in the mix here, and I want EC in the mix here. But I don't want AB because I don't see an AB there. And I don't want BC because I don't see a BC there. So now I'm going to start looking at these sides and seeing what I can change to what. So let's start with AB. Now AB is located here. And if you remember earlier, they told us it was a tangent. And they also told us earlier that this was a tangent as well. Now I know a theorem if I have 2 tangents. And that theorem is called tangents from the same point. If I've got 2 tangents that meet up at the same point, what I can do is conclude that their lengths are equal. So the length of this tangent is the same as the length of this tangent. So applied over here, AB will be the same length as AE for this reason, tans from the same point. And we just state that in our work like this, AB equals AE, aka they have the same length, for the reason of tans from same point. Now I can switch out this AB to an AE, and we're getting one step closer to getting this monstrosity. After we make that switch, we can see the only odd man out is BC. I don't want BC because it's not here. So I want to change BC to something. Now we can see BC, I have like 3 equal lengths inside of BC. So I definitely have the power to change that. So how we're going to state this is we're going to say BC is 3 times the radius. It's got 3 radius lengths inside of it. And now I've got to decide what to change this radius to. So over here, I don't want BC. I'm going to want another DE so that I can multiply DE times DE to get DE squared. And we can see that DE is a radius, my chum. So we're going to replace this radius with DE. Just like that. BC equals 3 times the length of DE. Now this BC, we're going to replace with 3DE. So you basically just rewrite this line, but instead of BC, you replace it with 3 times DE, because we have that statement over here. And now I'm just going to cross multiply quickly. So I'm going to take this up and I get AE times EC. And then I'm going to cross multiply the other side. So I'm going to take this DE up and I get 3DE times DE. And now once we've cross multiplied, we've got to kind of make this look like this. So it's quite easy to do that. DE times DE is DE squared. And then I just divide both sides by 3 and then I've arrived at the finish line. And just also at the same time, after I divide both sides by 3, I'm just going to switch the side so it resembles that format. Yes, this question was some other type of ho-ho, my bro. Okay, let's have a look where the 5 marks come from. First mark comes from the statement and reason associated with the corresponding sides in proportion of the similar triangles. The second mark comes from tans from the same point. You get marks for your statement and reason over there. The third mark comes from changing AB to AE. And the fourth mark comes from changing BC to 3DE. The fifth mark comes from this line over here after you cross multiply. And you do not get marks for the answer because that was given to you. Bringing us to the last question in the paper. We need to find the ratio of the area of triangle FDC over the area of triangle ABC. Let's get those triangles highlighted, my chums. Yeah, it's much better, ne? Okay, so I'm going to start off by writing this and an equal sign next to it. And after I do that, I've got to expand these areas with an area formula. Now in Matric, you have 2 formulas at your disposal to calculate the area of a triangle. The first one is our stock standard area equals half base times perpendicular height. So this is the one formula we can use, area equals half base times perpendicular height. And the second one is the area rule. And the area rule comes with terms and conditions. The small a and b represent sides, and the c is the included angle between those 2 sides. Now if you've got one triangle inside another triangle like this, and they share a common angle, it's always recommended that you use the area rule. So I'm going to expand both of these areas with the area rule like this. And after I do that, I've got to modify them to match these triangles. So let's start off with triangle FDC, our red triangle. So we have to use the common angle. Oh wow, and luckily it's C in this case as well. So we're going to be using the angle C in place there. So this little c can stay behind. Yes, what a good luck we had over there. Okay, now these 2 sides have to be the 2 sides that are touching the angle C. So in the red triangle, that will be side FC and side CD. So I'm going to change A to FC and I'm going to change B to CD. Just like that. And now I'm going to modify the green triangle to resemble that format. So in the green triangle, we're also using angle C in place here. So we've got to put the 2 sides that are touching angle C in the green triangle, which will be this side AC and this side CB. And now, once we've made those replacements, we're going to work on simplifying this a little bit. We can see we're multiplying everything at the top and bottom. So we've got one term over one term. So we can actually start cancelling things that are in common with the top and the bottom. So we can cancel the halves and we can cancel the sine of c's. After I cancel the halves and the sine of c's, I'm just left with the sides on top there. Now we've got to think back to what we did in the very first question where we got our scallops and ratios. And just to give you a quick reminder of that, we got the ratio of 2 to 3 on that side. We took it across the parallel lines with a line parallel to one side of triangle to get the ratio of 2 to 3 on this side. So FC over AC will have a ratio of 2 to 3. So I can replace this with a 2 and this with a 3. Conversely so, CD over CB, CD has a ratio of 2 and CB has a ratio of 3. So I can make those replacements. And after I do that, 2 times 2 is 4, 3 times 3 is 9. And we have officially wrapped up this question with a nice little bow and tie, my baby. Okay, so the area of triangle FDC over the area of triangle ABC equals 4 over 9. That is the final answer. Let's have a look where our 3 marks come from. Your first mark will come from expanding the areas with the area rule. And then the second mark comes from substituting the correct ratios of 2 over 3 and 2 over 3 inside of this line. And the last mark comes from the correct answer of 4 over 9. And that wraps up this nasty little June exam, my friends.